Hello folks, and welcome to today's video where we're going to talk about drawing Lewis diagrams for covalent compounds. They're going to look similar to Lewis diagrams for ionic compounds, but they are going to be slightly different. So covalent compounds are held together by shared pairs of valence electrons, which are called bonds. And these bonds are shown as a short line that is connecting the symbols of the two elements. Each atom that is to be connected must contribute a valence electron to the pair that will be shared between the two. If an atom does not have an unpaired valence electron, it cannot contribute to a shared pair and so cannot form any additional covalent bonds. This is one reason why it is very important when we are drawing the Lewis dot diagram for the neutral atom that we spread out the valence electrons before we begin pairing them up, because if we do that incorrectly, we'll be forming the wrong number of covalent bonds. Now remember that the reason that non-metal atoms are sharing these valence electrons is so that they can reach 8, right? They want to get to the octet of valence electrons. So these shared pairs, or sometimes called bonding pairs, count towards the octet of both atoms that they are shared between. So if we were looking at the fluorine atom on the left side of this molecule, it would have these 8 valence electrons, counting both of the electrons in the pair that it is sharing with its neighbor. Its neighbor also counts both of those shared valence electrons. And so by sharing these valence electrons, it enables each atom to get to the 8 that it needs in order to be stable. In addition to the shared pair, each of these atoms possess non-bonding or unshared pairs that are counted only towards their own total. So if we are drawing the neutral fluorine atoms individually with their 7 valence electrons, they already have these 3 pairs that they are not going to share with anybody else. And then they have 1 unpaired valence electron that they could choose to contribute to the shared pair. Now, each of the atoms in these drawings so far are connected by a single shared pair of valence electrons. And so they are called single bonds because there's 1 pair of electrons that's being shared. However, other atoms have the potential to share multiple pairs of valence electrons. So if we look at, for example, a pair of oxygen atoms with their 6 valence electrons, they have 2 unpaired valence electrons that they could potentially share together. And so when we draw their final molecule, which could look something like this, they are being connected by 2 pairs of shared valence electron. This would be called a double bond. And if we look at the nitrogen molecule, nitrogen atoms have 5 valence electrons. They have 3 unpaired valence electrons that they can contribute to shared pairs. And so when we have a nitrogen molecule, there are 3 pairs of valence electrons that are being shared between the 2 atoms. That is called a triple bond. So we can have a single bond like the ones that we looked at initially, or we can have a double, or we can have a triple. There is a hypothetical disputed quadruple bond. It was published several years ago that a group had observed a diatomic carbon molecule where they were sharing 4 pairs of valence electrons. But their publication was not widely accepted and hasn't been repeated. So we're thinking that this is just a hypothetical for now, not something that we observe in nature. So let's get down to walking step by step through the procedure for drawing these diagrams with a couple examples. So our first example is going to be NBr3. So nitrogen is in family 5A. So we would start by drawing the neutral atom of nitrogen with its 5 valence electrons. We would also draw the neutral bromine. Bromine is in family 7A, so we're going to need to put 1, 2, 3, 4, 5, 6, 7 valence electrons. Since we were given the formula here, we know that we're going to need 3 copies of bromine, so we'll go ahead and draw that out. Our next step is to connect any non-bonding pairs or non-shared pairs within the individual atoms. Nitrogen has a pair of electrons that are already paired up, so they won't participate in bond formation. And each bromine is starting with 3 pairs of valence electrons that are already matched up and won't be participating in bond formation. So we can go ahead and connect those just to make sure we don't accidentally draw them as being part of a bond. Once we've already knocked out the pairs that are not going to be shared, we can now look at the potential for shared pairs. So we've got our nitrogen. It has the most unpaired valence electrons. It has 3 singleton valence electrons. Each bromine only has 1. So the rule of thumb here is that we're going to take the atom with the most singleton valence electrons and put that in the middle. So we'll start off by connecting everybody to our central atom, and that actually uses up all of our unpaired valence electrons. Since we're all in pairs, it would be a good time to double check the octet of each atom. So the nitrogen started with 5, but it can also lay claim to all of the electrons that it's sharing with its neighbors. So all the electrons that are going to belong to nitrogen will be those ones. We've got 1, 2, 3, 4, 5, 6, 7, 8. And then for the bromines, they are also counting those valence electrons that they're sharing with the nitrogen. So that bromine started with 1, 2, 3, 4, 5, 6, 7, and then it picked up the one that is sharing with the nitrogens. So that one's good, as are each of the other bromine atoms. So we're ready to draw our final draft of this picture. Most people find legibility-wise that it's best to stick with right angles. So we might draw something like this. Again, putting the nitrogen in the center, connecting it with single bonds to each of the other atoms in the structure. Some people find all of these short lines confusing, and they prefer to draw the non-bonding pairs as dots, right? And reserve only the bonds for the short lines. So you might see something that looks more like this, with all of those non-bonding valence electrons shown as dots. Either is fine, it communicates the exact same information. Our next example is going to be carbon dioxide, CO2. So we've got carbon, which is in family 4A. So we'll draw it with 4 dots, one on each side. And we've got oxygen, which is in family 6A. So we'll do 6 dots. And then the formula tells us that we need 2 oxygen atoms. So we'll do a second copy of the neutral oxygen. The next step is to connect any non-bonding pairs that already exist. So the oxygens already have 2 pairs of valence electrons that are all paired up and will not participate in bonding. And now that we've done that, we can use the unpaired, the singleton valence electrons, to connect the atoms. Carbon has the most at 4, so we'll put it in the center. And now that we have connected all of the atoms, we have to deal with the fact that we still have singleton valence electrons. And so there are a couple options here. One option is to pair up the valence electrons that carbon has, but that would leave it with short of 8 valence electrons, right? If we count it as it is now, we have 1, 2, 3, 4, 5, 6 valence electrons that carbon can claim. It's still short of 8, as are the oxygens. So in order to help carbon reach its 8, it is also going to share a second pair with each of the oxygen atoms. So our final draft of this might look something like that, or that. Again, the carbon in the center is laying claim to all of the electrons that it is sharing with the oxygen atoms. The oxygens have electrons that belong only to them, but also lay claim to the electrons that are being shared with the carbon. So now everybody has 8 valence electrons. One thing that I have noticed people tend to do is they like to connect their atoms into rings. This is not a good idea. Rings are generally not stable, particularly if you only have 3 members of the ring. That's not really a ring, that's more like a triangle. So whenever possible, we want to avoid creating rings of atoms in our structure. So we would not see something like the carbon bonded to the oxygens in a ring like that. Not even sure how we would finish that structure. We'd avoid creating rings in our drawings. All right, folks, so that's all the information that we need in order to start creating the Lewis diagrams for covalent compounds. These diagrams can get more complex as more and more atoms are added to an individual molecule, but that basic procedure will steer you well in creating these diagrams as we work our way up. This procedure will enable you to draw diagrams for pretty much any neutral covalent compound. If you start venturing out into the world of polyatomic ions or organic compounds, your diagrams may change a little bit, and the procedures that folks use to create those diagrams may change a little bit. But this procedure will serve us well and enable us to understand at least what's going on in those other diagrams too. Thank you very much. Have a great day.